In the third lecture, we will introduce some common discrete and continuous probability distributions. Before we introduce the distributions, let's first review some related mathematics. Factorial of n, denoted by n exclamation mark, is the product of all positive integers less than or equal to n. It is widely used in the permutations. Factorial of n is the number of ordered arrangements of n objects. Permutations and combinations are two important concepts in probability theory. The difference between permutation and combination is ordering. The permutations are for lists where order matters, and the combinations are for groups where order doesn't matter. Typically, permutations and combinations are related to subset selections. For example, select k objects from a total of n objects to form an ordered list is k permutation of n expressed as pnk, which is factorial n divided by factorial of n minus k. For example, if we pick 3 letters from letters A to F to form a code, we have Pn equal to 6, k equal to 3, which are 120 unique codes because the order matters. And the code ACB is not the same as BCA. A k combination of n as C and K shows the number of ways to form a subgroup. In the previous example, we form 20 unique groups when we pick 3 letters from letters A to F to form a subgroup because there is no order in the subgroup. One of the basic discrete distributions is a Bernoulli distribution. The random variable takes the value 1 with the probability of p and 0 with the probability of 1 minus p. The probability mass function is this. The expectation of the distribution is p, and the variance is p1 minus p. Tossing a coin may give us a Bernoulli distribution of p equal to 0.5. If we have n independent Bernoulli trials instead of 1, and the random variable y is the event counts, then we have a binomial distribution. Binomial distribution counts successes out of n trials. This is the probability mass function. The sample space is 0 to n, and the third code item is the y combination of n. The expectation is np, and the variance is np1 minus p. For example, if we count number of heads when we toss a coin 10 times, then we have this result. It tells us, for instance, that the chance of only one head in the 10 trials is 0.98%. Poisson distribution counts events in an interval. It assumes that the event is infrequent, each event is independent, and the average number of events in an interval is a constant lambda. This is its probability mass function, and the random variable y is also event counts. Both the mean and the variance are lambda. A textbook example of Poisson distribution is number of soldiers accidentally killed by a horse kick. In the last slide, we introduced some discrete probability distributions. Now we will discuss continuous distributions. A continuous distribution is a distribution of continuous random variable with the number of possible values infinite and uncountable. First, we will learn exponential and gamma distributions. Both distributions are related to the Poisson process. When the random variable is the event counts in an interval, we have a Poisson distribution since it is discrete. When the random variable is the interval until the first event, then we will have an exponential distribution. The probability density function is this, with lambda is the average number of events in the interval. The mean of the exponential distribution is 1 over lambda, and the variance is 1 over lambda squared. The maximum of the PDF is always at 0, thus the mode of the exponential distribution is 0. The life expectancy of a light bulb is a daily life example of the random variable with an exponential distribution. We also may be interested in the kth event instead of the first event. If that is the case, an exponential distribution is generalized to a gamma distribution. The interval until the kth event in a Poisson process is a random variable with a gamma distribution. The probability density function is this, with k also known as the shape parameter. Here, gamma k is the gamma function, and if k is a positive integer, then it is the factorial of k minus 1. The mean of a gamma distribution is k over lambda, and the variance is k over lambda squared. The mode is k minus 1 divided by lambda, for k is equal to or greater than 1. The function is valid for non-integer positive parameters. The exponential and chi-square distributions are two special cases of the gamma distribution. When k equal to 1, it is the exponential distribution. And when lambda is 1 over 2, it is a chi-square distribution with degree of freedom 2k. Here is an interesting problem. A bank has an average 2 defaults each month. We would like to know the chance of no defaults in the next quarter and the chance of the 100th default happen during the 5th year. We may assume default is the event in a Poisson process. The average number of defaults lambda is 2 per month. The first question may be solved using the cumulative distribution function of the exponential distribution. Here is the CDF, capital Fy. We may derive it with calculus. No defaults in the next quarter means the first default happens at least 3 months later, which is Py greater than 3. The probability of no defaults in the next quarter is 1 minus the probability of the first default within 3 months. So Py greater than 3 is 1 minus F3. It yields a probability of about 0.25%. Thus, the chance of no defaults in the next quarter is about 0.25%. We may use the gamma distribution to answer the second question. The 100th default suggests k equal to 100. Mathematically, the 100th default during the 5th year is Py greater than 48 months and less than or equal to 60 months, which requires the cumulative distribution function of the gamma distribution. The problem is not easy without help from computer. Here we use Excel software. Excel has a built-in function, gamma.dist, with two parameters, alpha and beta. Alpha is k, which is 100. Beta is 1 of lambda, which is 0.5. The function returns the cumulative probability if the last flag is true, and the density probability if the last flag is false. Thus, F60 is 0.972 and F48 is 0.355. The difference is 0.617, so the probability that 100th default happens in the 5th year is about 62%. The example helps us to learn when and how to use the exponential and the gamma distribution. This slide shows the PDF of the gamma distribution in two special cases, exponential and chi-square. The left graph shows the PDF of the gamma distribution with k equal to 1, which is exponential, or lambda equal to 0.5, which is chi-square distribution. Here, the blue curve has k equal to 1 and lambda equal to 0.5. It is a chi-square distribution with degrees of freedom of 2, and at the same time, an exponential distribution with lambda equal to 0.5. If k equal to 0.5 and lambda equal to 0.5 as the brown curve, then it is chi-square distribution with degree of freedom of 1. In this case, the random variable is the square of a random variable with standard normal distribution. When k equal to 2 and lambda equal to 0.5, we have the purple curve. The mode of this distribution is 2, as shown in the graph. If k equal to 1 and lambda equal to 1, then it is the standard exponential distribution. The right graph shows the gamma distribution under various k and lambda. When k becomes larger, the shape of the function becomes more symmetric. In fact, the skewness of the gamma distribution is 2 over square root of k, only depends on k. That is probably the reason we name k the shape parameter. When k is large enough, the distribution converges to a normal distribution, which we will learn in the next slide. Normal distribution is also called Gaussian distribution. It is symmetric and bell-shaped. The probability density function may be written as this. where mu is the mean of the distribution and sigma is the standard deviation. The variance of the distribution is sigma squared, and the term y minus mu divided by sigma is called the standard score or z-score. From the expression, we know z-score is the number of standard deviations by which the value of y is above or below its mean. Since the distribution is symmetric and unimodal, the mean, median, and the mode is all at mu. The skewness and the excess curtices of the distribution are zero. When mu equal to 0 and sigma is 1, then we have the standard normal distribution. The graph shows the PDF of the normal distributions with various parameters. When sigma becomes larger, the curve is more spread out around the mean. In summary, we introduced some common distributions in this lecture. First, we discussed the three common discrete probability distributions: Bernoulli distribution, binomial distribution, and Poisson distribution. The random variable with the Bernoulli distribution takes the value 1 with a probability of p, and the value 0 with a probability of 1 minus p. The random variable with the binomial distribution is the event counts for n trials. The random variable with the Poisson distribution is event counts in an interval with an average count of lambda per interval. Then we discussed three common continuous probability distributions: exponential distribution, gamma distribution, and normal distribution. The random variable with the exponential distribution is the interval until the first event in a Poisson process with an average count of lambda. The mean and the variance of the exponential distribution is 1 over lambda and 1 over lambda squared. The random variable with the gamma distribution is the interval until the kth event in a Poisson process with the average count of lambda. The mean and the variance of the gamma distribution is k over lambda and k over lambda squared. When k is equal to 1, the gamma distribution becomes the exponential distribution. When lambda is 1 over 2, it becomes the chi-square distribution with 2k degrees of freedom. As k becomes larger, the shape of the function becomes more symmetric and will converge to a normal distribution. The normal distribution is symmetric unimodal and bell-shaped. The mean is mu and the variance is sigma squared. When mu is 0 and sigma is 1, it is a standard normal or z distribution.